NVMe fabrics. Great. Okay, so here's the agenda. I'm going to discuss the effort to standardize booting from NVM Express namespaces. Then I'll go into the architecture of the open source prototype, which demonstrates booting over NVMe over TCP. I'll then discuss an example design and reference implementation of booting of NVMe or fabrics in a UEFI environment. And then I'll conclude with where the spec prototype can evolve from where it is today. Spec and prototype, sorry. So let's get started. So NVM Express, it's an open collection of standards and information to fully expose the benefits of non-volatile memory in all types of computing environments, from mobile to data center. NVMe is designed from the ground up to deliver high bandwidth and low latency storage access for current and future non-volatile memory technologies. NVM Express Consortium was incorporated in 2014, and it currently has over 100 member companies, I think something like over 1,400 individual members. It's the consortium that's responsible for developing of the NVM Express family of specifications, which include our topic today, the NVMe Boot Specification. And this was published as version 1.0 on the NVM Express organization website in December of last year. And it's taken its place as part of the NVMe family of specifications. You can see a sort of family photo there on the right with the specification family members represented. The goal of the NVMe boot spec is, of course, to standardize booting, but from local and remote NVMe namespaces. The initial version of the specification, version 1.0, it concentrates on defining extensions to the NVMe interface for booting over fabrics, especially TCP, with the capability of expanding the boot spec in future revisions for standardizing of booting over other transports. The boot spec has a normative section, which includes general concepts for NVMe booting and mechanics, such as ACPI tables, to enable pre-operating systems and operating system environments to share configuration context. And it also has an informative section, which introduces boot stages and flow in a UEFI pre-OS environment, and also best practices for reliable OS consumption of pre-boot configuration and operating system and fabric specifics. And that's kind of what we're going to have a mini primer on today. So a bit of background and motivation. The NVMe Boot Task Group, which authored the boot spec, is currently comprised of 99 members from 36 companies, or at least as the last time I checked the task group roster. It's co-chaired by Intel and NVIDIA and Dell. A subset of the member companies of the Boot Task Group dedicated resources to develop an open source reference implementation, which we'll go into. And so the question is, why did so many companies work to develop an NVMe boot specification? And why were several of them willing to dedicate engineering resources to develop the associated reference code demonstrating booting over NVMe TCP? And frankly, the answer is because the lack of a standardized booting of NVMe and NVMe fabrics is a missing requirement for NVMe to take its place as the language of storage. And this lack presents a barrier for adoption, especially in large scale and dynamic deployments and composable disaggregated infrastructures and that sort of thing. The boot spec itself is a complex multi-component system comprised of elements from pre-operating system firmware and software configuration exchanges and operating system tools and applications and system configuration mechanisms. And as such, it is comprised of more than one standard, and it required cooperation of multiple ecosystem partners. First of all, I'll do this briefly. In cooperation with the UEFI forum, we developed the specification content to enable boot software for the UEFI and the ACPI environments. Next, in order to facilitate exchange of secrets and credentials for common NVMe over fabric connections that's utilized by both the pre-boot and the operating system, the existing Redfish secrets registry was extended to support NVMe or fabrics authentication and transport security credentials. And I have backup slides if people want to get more detail on what happened in the UEFI forum or the secrets registry for DMTF. But along with these efforts, of course, the Boot Task Group developed the NVMe Boot Standard and this public reference implementation that's based on open source frameworks that we're going to go into for the rest of the presentation. So since NVMe, it's in widespread use, has been for a while, for booting over PCIe, local booting, the first revision of the boot spec started with standardization of booting of NVMe namespaces over fabrics. And in order to speed the development and standardization of booting over NVMeR fabrics, we started with the TCP transport, and we leveraged the groundwork of booting over iSCSI. And this included adopting a very similar boot flow handover mechanism as used by iSCSI. iSCSI uses an ACPI iSCSI boot flow handover mechanism that it called the iSCSI boot firmware table, or IBFT, as its mechanism for sharing of pre-operating system configuration and context with the operating system. The NVMe boot task group, we developed a similar mechanism that we call the NVMe boot firmware table, the NBFT. Now, this picture, yes, it takes some liberties. It's a bit high level. It's meant to help folks that are familiar with the booting over iSCSI to understand how we leveraged iSCSI booting for booting over NVMeR fabrics. But let's go into a much deeper detail about the OS boot flow in a UEFI environment. The UEFI system specification defines several phases of the boot process. And here you can see on this very busy picture the 7 primary phases of the Tiana Core EDK2 implementation that's widely used today. This EDK2 implementation is what our proof of concept is based on. And as the boot spec and the reference implementation affected several of these steps, I'll go into brief detail about the relevant phases and narrate where booting from NVMe or fabrics fits into each phase. The first primary phase after the platform security completion is the pre-EFI initialization phase, the PEI phase. During this phase, amongst other things, the initial boot temp configuration is collected, and this includes subsystem information such as the NQN, IP addresses, and security parameters. Now, boot temp configuration is stored in UEFI variables, and this is currently done with an EFI shell tool, and that parses configuration file and reads UEFI variables. Now, in the future, there might be a more common EFI user interface for configuration attempts and BMC-based approaches for distributed computing and configuration in large data centers and fleets. That didn't quite happen for the proof of concept. This configuration, it's relevant to the pre-operating system driver and subsequent pre-boot phases, as well as being important, of course, for the later establishment of configuration context by the operating system once it starts to come up. Now, PEI is followed by the driver execution environment, or Dixie phase. In Dixie, drivers for the various devices and interfaces are loaded as protocols. And this is where the primary new work happened in our reference implementation. This is where we did have most of our effort was for the proof of concept. The driver reads the configuration from those UEFI variables. It sets up network configuration, and it connects to the relevant remote NVMe subsystems over those connections. And that's where we finally gather the namespace-specific information for later use by the boot manager. And at the end of this phase of driver load, this is where the configuration is stored in the ACPI NBFT table that can be accessed by the operating system once it starts to come up. Now, I want to digress briefly on one slide before we go into the next phase and discuss the NBFT and what's in it. The NBFT, it consists of a header, a control descriptor, a host descriptor, and some optional descriptors. The HFI descriptor list that's the indexable table of all the host networking details that you have. There's one NBFT, one HFI descriptor for each fabric on the host. And then you have the SNSS descriptor list, which is, again, another indexable table, and that contains the target and storage subsystem details and all the route relevant information for each of those remote subsystems. Now, while the published NVMe boot specification and reference implementation support in TCP, it is very possible to add support for additional transports, InfiniBand, what have you. To do so, it's really only necessary to amend the specification to add transport-specific accoutrements to the NVMe HFI transport information descriptor. And there's a minor mandatory header as part of the HFI transport internal descriptors that we have today, and then other transport descriptors and specific flags and configuration context is needed. I have a slide that details this if we have time. But for TCP, the transport specifics really are just things like MAC address and VLAN and IP addresses and gateways. Now, keep in mind that if a transport doesn't already have an existing implementation in the NVMe transport specs, it's not already a transport that's supported for NVMe, or if it's not in the UEFI specs or whatever, then you might need to have some extensions to those areas as well. But anyway, this is the minimum information that the pre-operating system driver needed to establish connectivity from a host to an NVMe or fabric subsystem and complete the pre-boot. And this information is later presented to the operating system as it starts to come up in this ACPI table as sort of a one-way means of communication, if you will, between the pre-operating system environment and the runtime operating system. Now, I do want to point out that an advantage of the NBFT over the iSCSI boot firmware table is the ability for the NBFT to share more than just boot namespaces with the operating system. And this can include non-boot namespaces, data stores that the operating system or workloads on that system might want when they come up. So they have access already to those data stores from those remote namespaces. All right, back to the boot flow. We're almost done here. Dixie, it's followed by the boot device selection, BDS phase. And this is where the boot manager entries are matched to EFI partitions via GWIDs. System policy controls which of these namespaces might be chosen as the boot device and in which order they're offered for booting by their EFI device path. Now, this is common practice, not something that we invented or touched. In some implementations, such as EDK2, a boot manager or other selection screen is typically found in this phase, and that's what I have an example of in the lower left. You'll probably recognize it. Boot managers usually help the user correlate specifics of the device in question to a boot attempt, and here you see that the boot manager found, an NVMeR Fabrics messaging protocol with a Linux distribution attached on the protocol that's represented by the block device. And the boot device selection phase is followed by the transient system load phase, which is where the operating system image is loaded and UEFI to OS execution handover is performed, or at least started. Now, this is called transient. It's transient because the UEFI might hand over the execution to other applications or drivers during this phase. However, access to the native connections that the UEFI pre-OS drivers originally created, it's still there and still possible. So this allows you as a bootloader, a grub, to interact with the NVMeR Fabrics devices that were previously attached without having to have their own driver present. And it also means that the transient load phase environments, they don't need to consume context from the ACPI NBFT, since the configuration context, it's still present. And it's also possible for drivers and applications in this phase to create new ACPI tables or table entries during this phase. I'll show you some tools that let you do that. By the end of this phase, however, the NBFT or NBFTs, if they're more than one, have been generated and stored in memory for runtime operating system access. And then with all that, we move into the runtime phase. Now, typically in runtime, the operating system is completely disconnected from the pre-operating system drivers, such as in UEFI. At this point, the operating system has a choice here. It might choose to read the NBFT in order to set up the appropriate networking interfaces, such as device selection or routing or binding, if it wants to reestablish that connectivity in the same way the pre-OS driver did, using the same options. Now, alternatively, the OS might choose to utilize both local administrative configuration and a subset of the content read from the NBFT in order to establish connectivity to devices configured during the pre-OS environment, if it wants to maybe establish access to different namespaces or a subset of those namespaces, or use different options. The OS still needs to configure any authentication or discovery that's relative to the network, and then it can reconnect to all those NVM subsystems, which enables access to the namespaces on those subsystems by other parts of the OS or applications or workloads running on that system. Now, hopefully I haven't bored you completely. Let's go on to the reference implementation specifics. Now, the implementation, it's based on UEFI EDK2 and the NVMe Boot Spec 1.0 to aid developers from across the industry to enable consistent booting over NVMe and NVMeR Fabrics. It was developed by a subset of the NVMe boot task group members, and this included Dell Tech, NVIDIA, Intel, SUSE, Red Hat, Hewlett Packard Enterprise, and VMware. And the code is released under the BSD3 clause, or mostly released under the BSD3 clause. There might be some subcomponents that require a different open source license, and of course we honor those. The reference implementation, it consists of both pre-operating system and operating system runtime software. And in the pre-OS environment, we have a new UEFI driver for the TCP transport for EDK2 that we developed, which produces those ACPI NBFTs prior to the OS boot phase. And then in the OS boot and runtime areas, there's a Linux reference implementation that exposes NBFTs and consumes the NBFTs that we developed that enables use by common OS tools. And again, I've got several slides that talk about those tools. Now, I'll start with a brief evolution of the proof of concept architecture towards the reference implementation. And then I'll go into those tools that support booting over NVMe or Fabrics. Hopefully I don't run out of time. Now, apologies for the busy slide, but it's important. This slide attempts to show how the design evolved from the initial concept to the reference implementation that exists today. On the left is our originally proposed concept architecture before standardization and before we started really talking to our ecosystem partners. There, in the blue, are items that were planned as new development for UEFI, NVMe, or fabrics behavior. And then in green are the elements that we believe we could leverage from the existing ecosystem components. And this included stuff like the implementation of NVMe or fabrics in SPDK within the EDK2 driver. Our initial concept, it was focused on the basics of the driver itself. We wanted to try to reuse the community assets, such as SPDK, so we didn't have to invent whole new stacks. I mean, the stuff was there, why not reuse it if we could? And on the right is what we ended up with. It's the implemented architecture of the reference implementation. And you can see where we modified or added to existing components. As the reference implementation evolved, we were able to develop an NVMeR fabrics library as a POSIX shim in EDK2. And that made it possible to directly reuse the SPDK NVMeR fabrics transport layer. And this meant we didn't have to create another bespoke ecosystem implementation with all those associated interoperability and maintenance problems. And we are very fortunate to have some members of the SPDK team look at our work and tell us whether they liked it, and they did actually approve of it. And this ultimately, it let us build an extensible EDK2 driver that lets us drive the frameworks. So those interfaces that you see in brown can be reused or developed from the EDK2 and allow us to reuse much of the existing UEFI interfaces that you see present there today. Again, you can see in the lower right there, the UEFI HII is crossed out because we didn't get to that one. So in addition, as I teased earlier, as we were developing the pre-OS driver, we found that we needed to be able to manage and interact and test this environment more rapidly. And so we created some configuration tools that made it easier to automate and interact with the UEFI pre-OS driver for testing. The primary new tool for pre-OS developers and administrators is a UEFI application called the NVMe-oF CLI. And this can be executed from within a classic EFI shell. And this command line tool was heavily inspired by the Linux NVMe-CLI. And it was designed to facilitate the same basic configuration and diagnostics that Linux has from the user space application available today. And this allows us to test out interoperability of the pre-OS reference driver. Couple of examples. The first one here, we have the NVMe-oF CLI command that provides a list of known NVMe fabrics devices that have been attached and their associated attributes. And this includes, as you can see, the namespace unique ID, it's a GUID, and the capacity of the namespace. And the second example here is of the NVMe-oF CLI EFI connect attempt command to connect to remote NVMe fabrics devices from the CLI. And this allows for the specification of target subsystem parameters such as IP addresses and subsystem NQNs and other controller-specific parameters. And that allows the user to set up and manipulate NVMe fabrics block devices during the transit system load phase. It enables developers or admins to connect to endpoints and create new block device connections on the fly to test them out, to debug them, and even boot from them from within this EFI shell. So very helpful. Now, leaving the pre-OS environment, let's talk about the transition into the final operating system runtime. For runtime in the Linux reference implementation, there's really three areas of concern. There's the platform, the kernel, and the user space. Most of the work, the new work there, it's in green. It's an effort to support the reference implementation in user space and leverages the existing ecosystem infrastructure that you see there in blue. Now, today, the Linux kernel exposes NBFT from ACPI via the sysfs interface to user space that you can see there. And the user space tools that start with extensions to libnvme and NVMe CLI allow for exporting and consuming the NBFT content, which I'll go into next. System management tools such as Drakit or EFI Boot Manager or even systemd, they can get standard representations from the NVMe CLI or libnvme libraries and use them to generate NVMe fabrics configurations to enable connection to NVMe subsystems and namespaces as normal. And all this development has been done using a standard KVM KVMU workloads using the EDK2 OVMF from the pre-operating system code that's available today. And this means that individual developers, they can simulate both the NVMe fabric subsystems and booting applications from within a single developer's instance. So this lets you grab the code quickly and test it out and play with it. So want to briefly digress into the two new subcommands we added to NVMe CLI. There's NVMe show NBFT, which dumps NBFT content, and NBFT connect NBFT, which connects to the subsystems and namespaces that are listed in or discovered through the NBFT. Now, these changes are being proposed for adoption upstream, and so it's possible the future structure of these commands might slightly change. But shown here is an example of the output from reference implementation running the show NBFT command. And the command allows both tabular human output and JSON output that displays the content from the BIOS in the NBFT. This example, it uses human output, and it shows two namespaces that are present on multiple controllers of a single NVMeR fabric subsystem that was found via its discovery controller by the pre-OS driver. Now note, this command, it does support reading custom NVMe NBFT objects in, and this is useful for developers testing the permutations of the pre-operating system administration configuration. And then this output, it shows NBFT CLI with all the NBFT descriptors in a structured machine-friendly JSON output that can be parsed by tools such as JQ. And it shows NBFT descriptors in their natural order without all that silly human-centric decoding and colonization. And as you can see in this example, the NBFT, it starts off with the required host descriptor, then followed by the subsystem descriptor records, followed by HFI, host transport interface, and lastly, the discovery structure, which contains the relevant discovery controllers. I think I'm going to be just about on time. The reference implementation is the result of a lot of different work coming together by a lot of people. It's useful to have multiple examples as the details of operating system bring up differ strongly from distribution to distribution. The proof of concept for booting of NVMeR fabrics, it's based on currently both OpenSUSE and Fedora distributions. The minimal prerequisites to enable the typical developer to be able to get started with interoperability in this environment, it's really either an OpenSUSE or a Fedora image, of course. You need a Linux host with a working KVM QEMU setup. You need virtual networking on that host. And then you need some sort of NVMe or Fabric subsystem as a storage device. And this could be just another QEMU virtual machine running the NVMe target software too, with at least something like 10 gigs of storage. Now we're wrapping up. The NVMe boot specification, it standardized the basic constructs to boot over NVMe and NVMeR fabrics. However, it's version 1.0 and more can be done. And so I'd like to see things like big data namespace quantity management in large fleets of namespaces and subsystems, multipath topology examples, supporting for a device tree, setting up of NVMeR fabrics boot entries in the OS, and very, very near to my heart is investigating booting of NVMe or fabrics over additional transports above and beyond TCP. Now, love to have people's help. The boot task group meets every Tuesday. Join if you're not a member of the NVMe, join it. If you are a member of the NVMe, sign up for the boot task group. Now, as far as reference implementation, that proves out the functionality of the NVMe boot specification by enabling booting of NVMe devices over TCP. However, it's a proof of concept. It doesn't implement all the features in the specification. And the specification is continuing to evolve with new capabilities and features. I think since we published the spec, we've had at least 3 technical proposals suggested. Now, examples of enhancements to the reference implementation that I'd like to see and invite involvement with include, but certainly aren't limited to, a human interface infrastructure tool for performing configuration tasks. I'd like to see support for authentication and transport layer security as defined in the NVMe family of specs for booting of devices. And I'd like to see support for the credential exchange using the DMTF Redfish secrets registry that I alluded to earlier. And of course, additional OS support. The more the merrier. Now, with that, and I really am very close to out of time for the break, I'd really like to thank you for your time. I really thank you for paying attention. And I'd really want to invite anyone to come in and join the community and help us continue to evolve this ecosystem. And as always, if you'd like to see any of the specifications that we've discussed, you can go to the links there. And thank you very much for your time. And I'll invite any questions if we run out of time. I am easy to find. And of course, there's a lot of people involved that could also help. So I'd like to open the floor. Okay, I see no questions. And so I would like to invite you all for the half an hour break. We will